The parameters for the building structure have different specifications that are appointed by the client. Group 22 has been instructed to build a portal frame with length 40 metres, width 14 metres, eave heights of 8 metres and a roof pitch of 6 degrees, with a rafter load of 10 kilonewtons per metre. Using the given BIM design brief, we can use our building parameters to allocate the correct size universal beams for both our columns and rafters as highlighted above. Additionally, Group 22 has been allocated Region B for wind loads. This gives the appropriate spacing for the purlins and girts. The double span C/Z 10,015 were chosen in order to fulfill the 1 kilonewton per metre load limit, while also saving costs on labour for bridging and over-engineering. Following the Australian standards and the LISAT installation guide, Group 22 fulfilled both needs. Furthermore, we had to address the client brief. This included at least 10 windows and 2 doors, a mezzanine level that covers 40 square metres with a 4-metre elevation that is accessible by stairs. Group 22 achieved this with a roller and sliding door and an 80 square metre mezzanine.
After constructing our model in Revit, we were then tasked to translate the design into a 3D space gas model whilst maintaining the same parameters. We utilised a structure wizard portal frame builder to construct the base portal frame with relevant length, width, base size, spans and pitch. The relevant haunches and members then had to be included in this model. Once the model was complete, we then had to run a linear static analysis to determine the relevant loads acting on the structure. Under the Loads tab, the data sheets under Member Concentrated Loads and Member Distributed Loads are now filled with data. We then proceeded to export this to Excel and remove any irrelevant data readings that we did not tend to analyse or compare. Next, all the data is pasted back into Space Gas in preparation to create various load cases. A useful way of examining our choices of members and connections is a design tool. The design tool allows us to check our portal frame structure in accordance with the AS4100 Australian standard and analyses the structure, recommending better performing alternatives for the selected members. This can be used not only on members but also the connections. Within our model, there are 3 main connections. For the apex connection, we selected a bolted apex connection where the purlins butt together and are bolted down either side. This connection is simple yet effective, preventing the 2 purlins from moving separately. For the rafter to column connection, we selected a bolted angle cleat. This is a strong commonly used connection within the warehouse industry, being very cost effective in comparison to other connections of similar strength. The column to concrete plinth connection is responsible for holding the frame in place. However, the holding down bolts with the base plate also prevent any lateral movement in the structure. Once the footing is poured, the timbers and the holding down bolts are stripped and the columns are bolted to this connection. However, in this instance, for the purpose of simplicity, we have chosen to consider the columns as being bolted onto the ground slab rather than the footings.
The analysis of the portal frame through Space Gas was conducted to understand and determine the forces acting on the structure. Using a combination of both the 3D and 2D models, the team had the ability to find the actions of our 5 primary load cases and a number of combination loads to simulate limit states of our structure. The primary load cases utilised in this analysis were dead load, G, which refers to the load of all structural components in the building; live load, Q, which refers to the loads that are not permanent and change depending on the uses of the building; internal crosswind, WCI, which refers to the wind factor affecting the structure's side from the inside, as opposed to external crosswind, WCE, that affects it from the outside. Internal longitudinal wind, WLI, affects the structure in the length direction of the structure, which is into the page looking at the 2D model. These loads could be combined with short-term and long-term combination factors to find desired limit states, as you can see on screen. The loads are also used in further limit states tests in accordance with the current Australian Standards 1170. By applying this analysis, the team receives a detailed evaluation of the limits of our build